Now, when we talk about the interrupt control registers, there are two sets of registers. One for the system exceptions, and those registers are from the system control block or the SCB. And for the interrupt inputs, other set of registers come from the nested vectored interrupt controller. Now, we will go through all the major registers that are required to configure and monitor the system exceptions and interrupts now. So, SCB to control these and NVIC to control these. However, the priorities that are being set for these two types of exceptions, that is system exceptions and interrupts, do interact with each other. So any priority that is being set for in the SCB registers will have an effect on the priorities that are set in the interrupt inputs and vice versa. So different set of registers, but we have to consider the entire set of exceptions and interrupts when we are talking about preemption and interrupt priority. Another thing, NMI, the top few interrupts don't have configurable priority, which we shall see shortly. We will go through the interrupts that are supported by our board, that is STM32F411XC board. So we will get a better idea of the number of interrupts it supports. So this is a generic diagram actually. Not all of the 255 interrupts will be present for any particular SoC. So we will get to see what are the interrupts that are actually supported. The AIRCR, or the Application Interrupt and Reset Control Register, provides priority grouping control for the exception model, and we are going to see this in detail in the later slides. It also controls the endian status for data accesses, that is whether it's big endian or little endian, reset control of the system. And to write to this register, you must write a 0x5a to the vect key field, otherwise the processor ignores the write. So this needs to be written first into the register, and then along with that you have to write the remaining bits that you need to configure in the register. Now the SHPR1 to SHPR3 are the system handler priority registers, and these registers set the priority level to 0 to 255 of the exception handlers that have configurable priority. Now we have to be aware of one fact here, that these system handler priority registers, that is 1 to 3 in the exception vector space, are byte accessible. In fact, in the NVIC space also, their respective priority registers are all byte accessible. Now, to understand these registers a bit more, let us go and have a look at the registers in the data sheet. So this is your system handler priority register 1. So there are 3 registers in total, and as you can see here, the first register controls the memory management fault priority. That is, it configures the memory management fault priority. It configures the bus fault priority and usage fault priority. The register 2 configures the SV call priority, and the register 3 controls the pend SV and sysdig priority. And these are the field names for the registers. There is one more interesting point that we will see in these registers, and the reason for that, the explanation for that will come in the later slides. That is, even though these registers are all 8-bit registers, for example, priority 4, priority 5, and priority 6, that is memory management fault, bus fault, and usage fault registers are all 8-bit registers, we only see that the top 4 bits are read write and the bottom 4 bits are read only. We are not supposed to we will even if we write something here, those writes are going to be ignored, and only what we write here is going to will be accepted by the Cortex M4 core. And the reason behind that is the priority grouping or only the top 4 bits of the priority registers are considered in the case of Cortex M4. Similarly, we have system handler priority register 2, which takes care of the SV call exception, and we have 8 bits again, of which the top 4 bits are configurable, that is read write, and system handler priority register 3, that is SHPR3, which handles the systic and pend SV exception. Now bit 0 to 15 is reserved and it must be kept cleared. So coming to the SCB exception control registers, the first register that we are going to look into is the ICSR, or the interrupt control and state register. This is a very important register for exception control, and it provides certain fields which we are going to see in the data sheet. So in short, it provides a set pending field for non-maskable or NMI exception. It has a set pending and clear pending bits for pend-SV and systic exceptions. And it also indicates the exception number of the exception being processed, whether they are preempted active exceptions, the exception number of the highest priority pending exception, and whether any interrupts are pending. So there is a lot of important information that is being conveyed by this register, and we set and clear some interrupts in the system exception range in the vector table. Now, one difference between this register, between the layout of this register and the register that we see in the NVIC, is that we will have pending bit set and clear fields in the same register in the case of SCB. But when we have a look at the NVIC registers, we will see that those registers are separate. That is, pending and setting the pending bit and clearing the pending bit are done in a separate set of registers, not the same register. Coming to the programming manual, that is PM0214 for the STM32 Cortex. So the information about the Cortex M microcontroller for ST is divided between mainly 3 documents. One is this programming manual, one is the reference manual that you have here, RM0383, and another one is the data sheet. So we will be referring to all these 3 documents in the course to extract the information that we need. So it's not in one document, but the information is spread across multiple documents. So that's something that you need to be aware of. Now, coming to that register that we are talking about. So let us try to find out ICSR here. So when you are faced with big data sheets and reference manuals, your best friend is the search bar in definitely the table of contents and the search bar, but the table of contents can again be quite overwhelming. So let us type ICSR here and try to see if we can locate that particular information on the particular register. So we seem to have found it, thankfully. So this is the register that we saw in the presentation also. So now we talked about this part. Now I'll do it only for this register and another one which need an in-depth explanation in the SCB. So, and we will go field by field, and we will try to understand what each field stands for, and then we can go through the other registers after this. So let us go from the lowest to the highest bit. Now we have bits 0 to 8, which is the vect active or active vector. So it is this field here. So the vect active is bits 0 to 8. Now what does that stand for? So it tells you which exception number is currently active. Now exception number means, let me get back to one slide so you will understand. So we know that exception number and IRQ numbers are again different. So an exception number for the exceptions and interrupts start from 1, but the IRQ number, as you can see, starts from -14, right? And that register gives you the exception number, not the IRQ number. So if you want to find out what the IRQ number is, that is, and that register actually informs about all the exceptions, not only this. Though it's a SCB register, it talks about all the exceptions. So your system exceptions as well as interrupts are going to be depicted in that particular field. So if you want to know which exception number you are in, which starts, you can check that field. But if you want to know which IRQ number you are in that field, what you need to do is, the moment you reach number 16, so you have to put in a logic there. That is, the moment the number is 16 in that field, you have to subtract 16 from that number so that you get a value of 0 and then 1 and 2 and so on. So that is something that you have to keep in mind if you are using that register to check which IRQ number is active currently. Coming back to the manual, the second bit of interest is bit 11, which is called read to base. Now read to base or return to the base level indicates whether there are preempted active exceptions. So 0 means there are preempted active exceptions to execute. Okay, and 1 means there are no active exceptions, or the currently executing exception is the only active exception. Okay, so this will give you some information about whether any preemption is about to happen or not. Then you have another bit called vect pending. Okay, and this talks about the pending vector or pending interrupts or exceptions that are in the queue. And it doesn't tell you about everything. It tells you about the highest priority exception number that is there in the queue. Okay, so 0 means no pending exceptions, and other values means it's the exception number of the highest priority pending enabled exception. Okay, the value indicated by this field includes the effect of the base pry and the fault mask registers, but not the effect of the pry mask register. So if you are even disabling all the interrupts using the pry mask register, still you will see the values here. That is, if there is any pending interrupts, the value is going to be depicted here. So we will see more about the pry mask register mainly. So we will be using the pry mask register in our application when we disable and enable interrupts, when we are doing some configuration of maybe the PLL or the system tick timer and so on. So this register is going to be used. We will not look into this particular bit field, but pry mask is going to be used. So just for your information. ISR pending is the interrupt pending flag, including NMI and fault. So it just informs you whether any interrupts are pending or not. Then bit 22, 23, 24 are reserved, but some bits, even though they are reserved, you must still keep them cleared. That is, if you write something here, there might be some undesired outcomes. So it's better to keep these bits cleared. It should be. Then you have the pend st clear. So this is a cystic exception clear pending bit. It is a write only. That is, if the cystic exception is in pending state, writing a 1 here removes the pending state of the cystic exception. So this one is, again, this can be controlled using user programming. And then you have the pend st set bit, which is the cystic exception set pending bit. So opposite of this, that is, if you write a 1 here, your cystic exception state is set to pending, and it is a read also. That is, if you write something here, you can read the value back. In this case, if you write something for clear, you cannot read the value back. The bit 27 is pend sv clear. That is pend sv. So I'm sure you're getting to see a pattern now. You have a clear and you have a set bit field following it immediately for that particular interrupt. So pend sv, again, it's clear pending bit, removes the pending state of the pend sv exception, and then you have the pend sv set pending bit. Okay, again, one states state to pending, and of course you can read from this register, but you should not read from this register. Whatever value you get is not the actual value that you have written in. And then the last one is NMI pend set. That is, it is setting the NMI exception state to pending. Okay, non-maskable interrupt. And since this is the highest priority interrupt, the Cortex M4 processor is going to try to get into this exception as soon as possible. Okay, and the moment it gets into this exception, this bit is cleared to 0. This is a summary of the ICSR register. We will be seeing this register when we are looking into code, but we will not be using this register to that extent, because yes, we will be using the cystic interrupt, but this register will not be used exclusively in our application, but it might come up once in a while. Next in the group of registers in SCB is SCB exception control registers is VTOR, or vector table offset register, and it is used to relocate the exception vector table to a different memory location rather than in the code section, in the code section or SRAM. That is, the exception vector table is located in the, to begin with, the exception vector table is located in the first region, in the starting region of the flash. But if you want to relocate the exception vector table somewhere else, then you can use this particular register to have that address entered here in this field from 9 to 29, and of course it has to be aligned to the size of the table. Lowest is 128 bits, and you can move your exception vector table to a different location in the memory. One thing to remember is the number of interrupts is product dependent. So though we saw a generic exception vector table which talks about 255 exceptions, it depends on the SoC vendor and the SoC make. For example, for our STM32F411, we will not have 255 interrupts. We'll have a lesser number of interrupts that are supported. So to see the exact number of interrupts that are supported and what interrupts are supported for this particular SoC, we have to go to the reference manual. The reference manual is RM0383, and in this chapter, interrupts and events, that is chapter 10, if you scroll down, here is the vector table for STM32F411X C/E. Now, as you can see, there are the number of IRQs. Now the number of exceptions are going to be the same for every Cortex M4 core. So there is no, it will not be different. But as far as NVIC interrupts, or rather the interrupts that are controlled by the NVIC are concerned, the number of interrupts are going to vary between different microcontrollers. Now I have marked interrupt number 6 because we are going to work with external interrupt 0, but then this was not there in the data sheet. So I have made some annotations and put in some comments here and there. So this is your IRQ number, which starts from 0 and goes down as you saw. Now these 3 interrupts are fixed. So let us have a look at the columns here. So this is the interrupt position, this is the default priority of the interrupt, and type of priority, acronym description, and the address in the interrupt vector table where that address of that particular ISR can be written. So now even if the address is shown as 0 here, for STM32F4 again, the flash memory starts from a different address. So this interrupt vector table will be located in the beginning of that flash area. So this address is not going to be 000000000. It's going to be something else, right? So that's something that we have to keep in mind. And the top 3 interrupts, that is the reset, the NMI, and the hard fault, as you can see, have priority -3, -2, and -1. That is the default priority of these interrupts. Now they are in negative to show that they are highest priority interrupts, and these priorities cannot be configured. They are fixed priority. Only from mem manage can we configure the priority of these interrupts. So that is the reason why it is all written as settable. So right from 0, that is a priority 0. These are the default priorities, of course. So all these interrupts are settable. So even when we get into the region of IRQs, we see that they are settable. So we can, and of course, bear in mind that here we set the priority of these interrupts in the SCB register, as we saw, and we set the priority of these interrupts in the NVIC registers. But when preemption happens, like we discussed previously, the entire set of interrupts are considered. So if you set some priority in the exception and if you set some priority here in IRQ, both of them are going to interact. So if this is higher, this is going to, this interrupt number, say SV call is triggered during EXTI21, or vice versa. If EXTI21 is higher than SV call, then this is going to be preempt the SV call, so on and so forth. So we'll see all that later. So this is, if you want to see the actual set of interrupts that are supported, then you have to come here. Okay. So for example, for STM32F407 discovery board, again, if you come to the reference manual for that particular board and go into the interrupts and events chapter for that particular SoC, then you will see that the number of interrupts supported will be again different, but this one is going to be same. This part is going to be common between all interrupts, the grayed out area, and that is up to here. So up to SysTick it is all the same, though, and for all STM processors again the start address is different. The NVIC interrupt control registers are another set of registers which configure and control the interrupts and not the exceptions. We have the ISER, or interrupt set enable register, and there are 8 interrupt set enable registers ranging from the number 0 to 7, and what these bit fields do is enable the particular interrupt that this particular bit field corresponds to. So this is interrupt number 0, interrupt number 1, and it goes on. Now Suppose if there is a pending signal for an interrupt, and if the interrupt is not enabled here, then that interrupt is not picked up for execution. That is, that interrupt is not activated even if it's a high priority interrupt. The next set of registers that you have, again 8 registers, is the interrupt clear enable register. Now these are used to disable the interrupt. So enabling the interrupts and disabling the interrupts are from separate registers. So if we enable an interrupt here by writing a 1, we cannot disable the interrupt by writing a 0 here. We have to come here and write a 1 where we wish to disable the interrupt. So if we want to enable interrupt number 1, we have to write a 1 here in the interrupt set enable register. But if we want to disable it, we have to come here to the ICERX, that is interrupt clear enable register, and we have to write a 1 here. So that's something we have to keep in mind. Now this is again the interrupt set pending register. We saw a similar register in SCB as well, but that register had a lot of functionalities in that single register. But in this case, this register is only responsible for setting the pending state for a register through software. So writing a 1 here, and of course reading this register will give you the state of the pending state of the register if the pending state is set by hardware. So writing a 1 into any of these fields are going to set that register to pending state. So this is going to be either set by hardware, or if it could be set by software, to software control the registers. Then you have interrupt clear pending registers. That is where we write a 1 to clear the pending status. So suppose if the hardware sets the pending status in the set pending register, we can actually come here and clear the pending status. And we will see different combinations and the different ways in which the interrupts behave depending on many factors later, as to whether if we clear the pending status by software, it could again get set because the interrupt is still asserted on the interrupt line, so on and so forth. We'll see all that later. Then you have the interrupt active bit register. Now this one actually depicts which are the interrupts that are active currently. So IAPR, and again there are 8 registers in this set of but these registers are again they are not byte accessible. We must be aware of that. Now these are 32-bit registers, and we have to do a read, modify, write for all of these registers. Now again, this is the interrupt priority register as we saw in the SCP, and these registers are again byte accessible, and you have 59 or 60 registers which are byte accessible, and they provide 8-bit priority fields, and for each of the 240 interrupts, and every register holds 4 IPN fields. Now it is not shown here, but like the SCB, these registers will also have their fields divided into 4 bits and 4 bits, and we can only write into the upper 4 bits, and we are barred from writing anything, or rather the lower 4 bits are actually ignored even if we write anything in there. So because the upper 4 bits are considered as the interrupt, upper 4 bits are used for interrupt priority grouping and sub-priority grouping. So that is something that we need to keep in mind. So even though these registers are shown as 8-bit fields, we are only writing the top 4 bits for these registers. The Cortex-M processors have a number of programmable registers for managing interrupts and exceptions. Now, most of these registers are inside the NVIC and system control block. But these three registers, that is pry mask, fault mask, and base pry, are outside of the NVIC and system control block. These are control registers, and they don't fall in a memory mapped region. So they have to be accessed differently. And they are some registers which are used to manage interrupts. Rather, they are registers which are used to mask interrupts in different ways. The NVIC and SCB, that is the nested vectored interrupt controller, and the system control block are located inside the system control space address range, that is 0xE000E000, and the SCS address space is of size 4 kilobytes. Now, after reset, all interrupts are disabled and given a priority level value of 0. So after every reset, we will need to configure the interrupts all over again, and that is done in the initialization process. Setting up interrupts are done in 3 steps mainly. So these are the 3 steps that are always followed when an interrupt is being set up. That is, the priority level of the interrupt is set. Now, this step is optional, but we will be setting priority levels of interrupts because we will be dealing with more than one interrupt, and interrupt preemption also is of importance as far as our applications are concerned. So this step, though this step is optional, that is, you can do away with it if you are dealing with a simple interrupt structure, we will be needing it. Then now when we have to enable the interrupts, it is enabled in 2 places actually. One is the peripheral for which we are enabling the interrupt, and another one is in the nested vectored interrupt controller. Okay, so 2 places. So either of them will not work. So you enable one and you keep the other disabled, the interrupt is not going to be enabled. There are other interrupt control registers also, but these are the 3 primary registers that need to be configured if you want your interrupt to work at all. Now, coming to the pry mask control register, this is used to mask. So masking an interrupt is basically disabling all interrupts. In the case of pry mask, it is disabling all interrupts except for the NMI, that is non-maskable interrupt, and the hard fault. So it changes the current priority level to 0. That is, anything above 0, that is anything with a lower priority than 0 is masked. Okay, and here is the assembly code for disabling and enabling the pry mask interrupt register. We will see it more in our code, and as we discussed, these registers are not memory addressable, so they will have to be addressed through assembly code. So we'll have to have some inline assembly in our C code. We had discussed previously, and I said that you can absolutely do without assembly coding in case of ARM Cortex M4 programming, but then again, it will be needed here and there for accessing certain control registers and so on. Next interrupt masking register is called the fault mask. Now, the fault mask register also is like the pry mask, but it masks even the hard fault interrupt. So it sets the priority level to -1. So only the non-maskable interrupt is allowed to is active. Rest of them all are masked. Now, the reason why you would want to mask all the interrupts is for time critical tasks. That is one thing, and secondly, for shared resources. If an interrupt service routine and a thread is sharing a particular resource, and you want a particular area of code to not be interrupted because it will cause certain error conditions where you probably will have the shared resource being overwritten by the interrupt, and it will probably have a different value from the one expected. uh, that is not desirable. So we generally disable the interrupts when we are in a critical section of the code. So this is the fault mask, and then there is another masking register. This also does not have a memory map. It is called the base priority. So base priority is, it disables all interrupts lower than a certain level which can be set. So the previous two, the levels are fixed. For example, one is 0 and one is -1. Prime mask only keeps the hard fault and the NMI enabled. Fault mask only keeps the NMI enabled and disables everything else. In base pri, you can actually set whatever priority you want, below which all the interrupts are going to be disabled. So say there is an interrupt, you want to disable interrupt priority from 0x70 to 0xFF. So 70 to FF in the interrupt vector space will all be disabled, and only the interrupts above that are going to be serviced.